So in this final video, let's use the concepts of molality that we talked in the previous video, along with the concept of freezing point depression to determine the freezing point of a solution. So this is similar to the freezing point experiment that you did earlier in the semester. So let's say we have pure glacial acetic acid, and I give you that it has a freezing point of 16.6 degrees Celsius. So I have a pure solvent and I give you the freezing point. To a 52-gram sample of that solvent, I add an impurity, a solute, specifically 14.5 grams of benzoic acid. I have the structure here just to be complete, but I've given you the molar mass here as well. That will be helpful. So I have 14.5 grams of this benzoic acid in 52 grams of the solvent, glacial acetic acid. I want to know what the new freezing point is of this acetic acid, benzoic acid mixture. I give you the freezing point constant for acetic acid. So that constant, just to note, the units are kind of funky. In the numerator is degrees Celsius. And the denominator is the unit molality for molality. So that constant has derived units. That's due to how it is calculated. You'll see that will be helpful in setting up this problem shortly. So I give you that Kf value. I give you the I value for benzoic acid. I want to know what the new freezing point is of that mixture. So you think, okay, I have a solvent with an impurity. So adding an impurity to a solvent should lower the freezing point of the pure sample. So I know my new freezing point is going to be the freezing point of my pure solvent, or the 16.6, minus the amount of Celsius, the amount of temperature that the benzoic acid lowers that solvent, delta TF. Once I calculate that and subtract these two values, then I can get my new freezing point. So we can easily calculate delta TF by the equation that was given 2 videos ago. The freezing point depression is equal to that constant Kf multiplied by I, which is 1, multiplied by molality of the solution. So I give you K sub F and I give you I, but I do not specifically give you the molality, so we will need to calculate that. So remembering that molality is moles of solute per kilogram of solvent. I'm first going to find my moles of solute, specifically the benzoic acid, by taking my grams of benzoic acid and using that molar mass appropriate and writing that appropriately so my gram units cancel. I'm left with my moles of solute. I need to take that and divide by my kilograms of solvent, which is the acetic acid. I have 52 grams of that. Converted to kilograms gives me 0.052. Dividing those two numbers will give me the molality of my solution. So my molality, when doing that division, is 2.3 moles per kilogram, or we use that M as a symbol. So I now have my molality. I have my K sub F. I have my I. I can go ahead and calculate my freezing point depression by multiplying those 3 numbers together. So my molality units cancel. My I value, there's no unit on it. I'm left with degrees Celsius, which is good because you would expect a change in temperature to be in degrees Celsius or some temperature scale. So doing that multiplication gives you 9.0. That is the amount of temperature, that is the amount that the freezing point is lowered from the original freezing point. So that's our delta TF. So that means our new freezing point is the freezing point of the pure solvent, the 16.6, minus delta TF, which we just calculated is 9. And so our new freezing point for our glacial acetic acid benzoic acid mixture is 7.6, which is lower than what we started with, which is what we expect, because when you add a impurity, that lowers the freezing point. If we were to do a similar calculation, but with regards to the boiling point of acetic acid, we would add that 9.0, because when you add an impurity, what does that do to the boiling point? It doesn't depress it, it elevates it. But we're talking about freezing point here. Adding an impurity lowers the freezing point, so that's why we subtract.